Traditional fraud examination and audit frameworks rely on linear causality. Every step of an investigation requires replicable logic and a verifiable chain of custody. If an examiner follows the exact rules and inputs, the outcome must not materially vary. Large language models operate on an entirely different architecture. They generate outputs through stochastic approximations, a process governed by random probability distributions. Here, the next word is a statistical guess rather than a calculated logical step. This diagram represents the collision of these two systems. Transformer models do not possess internal logic trees or verified databases. Instead, they navigate high-dimensional probability spaces, selecting outputs based on statistical correlations learned during pre-training on unverified data. They generate text by prioritizing token entropy reduction. The model selects the next word to minimize randomness and maximize linguistic smoothness. The system optimizes for lexical coherence and syntactic fluency, not for factual or procedural truth. Because the output often appears grammatically precise, professionals mistake this probabilistic construction for procedural fidelity. This is the determinism illusion. In reality, unless the model is explicitly constrained, the same prompt may yield different answers and different reasoning paths every time it is submitted. Mistaking syntactic fluency for evidentiary validity creates an epistemic rupture. If an investigator accepts a model's statistical simulation as a conclusion, they risk importing unverified artifacts into formally regulated legal environments. When asked to provide authority, an unconstrained model will simulate citation formats. It will construct regulatory codes or fabricate case facts through stochastic interpolation, connecting unrelated data points based on learned patterns rather than retrieving actual records. This fabrication violates the core ACFE requirement for verifiable source attribution. A simulated reference gives the illusion of factual authority, yet it lacks any grounded connection to time-stamped or jurisdiction-specific source material. Furthermore, an AI cannot provide an audit trail. The internal decision logic of the model, billions of parameter interactions across hundreds of hidden layers, is completely and fundamentally opaque. The forensic examiner has no way to show exactly how or why the generative model reached a specific detailed conclusion. Audits demand a strict chronology of verifiable facts. A generative model only provides a trace through a high-dimensional vector space. This path cannot be audited or challenged, making the output difficult to defend under cross-examination. These systems also suffer from temporal instability. Because models undergo continuous fine-tuning, a prompt issued today may yield different results. This undermines the permanence of output required for legal defensibility and audit documentation. An unconstrained model is a liability. It is structurally incapable of serving as an investigative oracle because it lacks causal transparency. To be useful, it requires an external containment architecture. Grounding an AI in a forensic environment requires the 3T model. This framework manages three interacting constraints: the token, the training of the model, and the training of the user. The first constraint is the token. Both inputs and outputs are computed in atomic units called tokens, which are capped by a fixed context window. This window is the hard limit on how much information the model can process at once. As the context window overflows, the model loses its semantic anchoring. Exceeding the token budget causes the attention mechanism to drop earlier instructions. This leads to missing data and silent hallucinations, where the model fills in the gaps with plausible but unverified details. The second constraint is the training. These hollow blocks represent the model's internal data. It contains statistical approximations of language, not cognitive knowledge. It mimics the structure of an expert document without possessing any mechanism for semantic verification. The final constraint is the user. Unlike deterministic software, the model responds variably based on prompt syntax. Vague instructions increase the randomness of the response, making the user's ability to frame the query the primary variable in the system's success or failure. An AI's forensic reliability is fundamentally capped. It is only as reliable as the token budget and the specific data distribution it was trained to simulate. To force the model toward consistency, we must use three mandatory risk dials: temperature, top K, and top P. These mathematical settings allow us to control the model's entropy, or its level of unpredictability. Temperature controls the randomness of word choice. A setting of 0.3 or lower pulls the probability mass to the most likely tokens. This suppresses creative, speculative elaboration and ensures the model provides repeatable, cautious outputs. Top K sampling restricts the model to only the top-ranked tokens by probability. Setting this value to 50 or less acts as a form of lexical censorship, slicing away the long tail of outlier words that are often responsible for hallucinations. Top P, or nucleus sampling, dynamically adjusts the token pool based on the cumulative probability of the next word. A threshold of 0.8 restricts variance even further, preserving semantic discipline across long investigative reports. Together, these settings strip away the model's creative variance. They force the system into a deterministic state where it can generate the same result from the same prompt across different sessions. This creates a significant risk for black box systems where these parameters are hidden. If the settings are undisclosed, the results cannot be independently validated, making them unsuitable for any formal audit trail. Parameter containment ensures that an investigation remains repeatable. Without fixed settings, the model's output is effectively random, which prevents the independent validation required for any formal forensic report. Beyond mathematical limits, the examiner must manage the hallucination-free forensic workflow. This requires moving away from single, massive prompts and toward a structured, segmented chain. This diagram breaks down the hierarchy needed to prevent drift. A chained sequence isolates each investigative step. Rather than asking the AI to find fraud in one go, we separate the process into discrete, verifiable modules. The anchor block establishes the forensic role and lexical rules. The parse block restricts the model to simple data extraction from ledgers or logs. By isolating the extraction phase, we prevent the model from interpreting data before it has been properly surfaced. We then use reverse querying to evaluate anomalies. Instead of asking the AI to guess who committed a fraud, the examiner provides the known outcome, such as an unauthorized payment, and asks the AI to list the plausible procedural breakdowns that could have allowed it. Every response in this chain must be governed by epistemic modesty. The model must be instructed to tag its outputs as theoretical simulations and explicitly state when the available evidence is insufficient to form a hypothesis. This structured approach ensures that every AI-generated suggestion has a traceable lineage. Each step is logged and anchored to verifiable data, creating a pathway that can be reviewed by audit supervisors. Continuous monitoring of the AI itself is required to distinguish true forensic signals from algorithmic noise. This is achieved by tracking two key stability metrics, burstiness and entropy. This diagnostic matrix tracks the health of the detection engine. Burstiness measures the temporal clustering of alerts. High burstiness in this quadrant indicates a surge of flags in a short time, often a sign that the model is overreacting to a benign, repetitive data pattern. Entropy captures the dispersion of the model's output. High entropy means the model is flagging the same underlying behavior inconsistently across different iterations. This signaling is erratic and undermines the reproducibility of the investigation. When burstiness and entropy both spike, the system enters a redundancy loop. The model persistently reflags the same entity without adding any new evidentiary value, creating an algorithmic echo chamber that wastes investigative resources. This can be masked by semantic drift. Drift occurs when the AI rephrases its alerts across iterations, making old flags appear novel. Without content-aware deduplication, the audit team may unknowingly review the same non-issue multiple times. Effective monitoring requires these diagnostic status checks. Without tracking these metrics, an AI flagging system can quickly degenerate into a source of procedural clutter and alert fatigue. These technical layers, token limits, parameter settings, and structured chains, combine to form the unified forensic sandbox. This environment provides the discipline necessary to move AI from experimentation into professional audit workflows. This sandbox transforms the AI from an autonomous oracle into a traceable simulator. By enforcing these constraints, the model's behavior aligns with the evidentiary standards of documentation and procedural transparency required for forensic reports. Within this controlled space, the AI can perform weak signal detection. It scans across thousands of records to find low-frequency anomalies, like slightly shifted payment rhythms or recurring but immaterial vendor changes that do not cross the thresholds of traditional static rules. It identifies hidden hierarchies by analyzing communication metadata and approval patterns across disparate silos. By constructing behavioral fingerprints, the AI can surface clusters of collusive activity that appear normal when viewed as isolated transactions. Firm. Despite these capabilities, the human examiner remains the central authority. No output from the sandbox is ever accepted as an investigative finding until it has been independently triangulated against primary source documents. The AI identifies the probabilistic irregularity, but the human auditor must provide the deterministic proof. Properly constrained AI allows an organization to transition from periodic sampling to the full population analysis of ledgers, contracts, and communication logs. This shift significantly improves the chances of detecting evolving fraud archetypes. However, the determinism illusion remains. Syntactic fluency is a facade. It sounds authoritative, but is hollow. The examiner must maintain professional skepticism even when the output appears certain. Constraining the model allows for the monitoring of massive datasets in real time, but this capability only serves the audit when the probabilistic engine is locked within a deterministic grid of professional standards. The forensic examiner remains the primary agent, using the AI as an inference tool to highlight patterns that then require manual verification and judgment. AI's true utility in fraud analytics is realized only through uncompromising structural discipline.